Greetings to all. Today we are going to present our design regarding the combined gas steam power cycles. We will assign to design a combined gas steam cycle power plant which can generate 500 MW to the new Lumut naval base and its town. Before we go to the solution, let's first look at the design of the power plant. To achieve 500 MW, we have designed a combined gas steam power cycle that consists of a boiler, compressor, heat exchanger, pump, condenser, gas turbine and 3 steam turbines. The assumptions made for this design are as shown. The power plant consists of two cycles which are gas cycle and steam cycle. The gas power cycle follows the concept of Rankine cycle, whereas steam cycle follows the concept of Rankine cycle. For the gas cycle, first the boiler receives heat from the source and then it heats up the air to higher temperature which is transferred to the gas turbine. The air rotates the gas turbine where the mechanical energy resulted from the rotation is turned into electrical energy. The fluid flows through the heat exchanger, compressor and return to the boiler again. As gas turbine operates in high temperature, the gas leaving the gas turbine is used as an energy source for the steam power cycle. By using the heat exchanger, the heat is transferred to the steam power cycle which heats the water to steam. The steam enters the steam turbine at high pressure and leaves the steam turbine at low pressure, where the state of the working fluid is saturated mixture. Then, it enters the condenser where the heat is ejected to the sink. The state of working fluid that leaves the condenser is compressed liquid. Next, the fluid enters the pump and leaves the pump at higher pressure. Finally, it enters the heat exchanger and the cycle repeats.
For the calculation part, we will begin by finding the work output for a single steam turbine. We have the input at state 1 and the output at state 2. In state 1, the input temperature is equal to 700 degrees Celsius and the pressure is 30 megapascal. Since the working fluid is water, from table A1, the critical temperature of water is 374.1 degrees Celsius. Here, we can see that the input temperature is higher than the critical temperature. Therefore, the state of water is superheated vapor. Referring to table A6, we can list out the properties of the fluid as shown. Move on to state 2. We first assume that the pressure ratio of the steam turbine equals to 3000. Then, we use the pressure ratio formula to find the pressure output, which will be our P2. Refer to table A5 at pressure 10 kPa. The output temperature T2 will be equal to the saturation temperature, which is 45.81 degrees Celsius. We can also obtain the properties of the fluid as shown from the table. Since the steam turbine is under isentropic process, the inlet entropy S1 is equal to outlet entropy S2. And here, notice that the value of S2 is in between the value of the liquid entropy and gas entropy. Thus, this concludes that water at state 2 is saturated vapor liquid mixture. With this information, we now can calculate the enthalpy at state 2. Using the average entropy formula to obtain the quantity, then using the average enthalpy formula to calculate the H2, we obtain H2 equals to 2081.559 kJ over kilogram. Finally, we can calculate the work output. First, we do the energy balance equation as shown. We will end up with the work output equals to H2 minus H1. Substitute the value and we manage to obtain the value of work output from the steam turbine equals to 1662.34 kJ over kilogram. Next calculation will be involving the output of the compressor. Based on reference, it is stated that to have an effective heat transfer, there should be at least 10 degrees Celsius temperature difference. Assume that the temperature difference between the surrounding and the steam temperature in condenser is 50 degrees Celsius. Since the average temperature of Lumut is around 25 degrees Celsius, the output temperature of condenser will be 40 degrees Celsius. Since the condenser undergoes isomeric heat rejection, the pressure inlet of condenser is equal to pressure outlet of condenser P2 equals to P3 equals to 10 kPa. Refer to table A4, we obtain the outlet pressure P3 equals to the saturation pressure of fluid when temperature at 40 degrees Celsius. As P3 higher than P saturation, the state and outlet of condenser is compressed liquid, which also means its properties are temperature dependent. The property of the fluid are as shown. All information we can proceed to the next component device, which is the pump. Since the process at heat exchanger is isobaric process, the pressure at the inlet of heat exchanger must be the same with the outlet pressure of heat exchanger, where P4 equals to P1 equals to 30 megapascal. Based on table A1, value of critical pressure of water is 22.06 megapascal. Since P4 is higher than P critical, the state of working fluid at outlet of pump is compressed liquid. Now, we can compute for the work input by the pump. By using the equation for work input, we managed to obtain the value for work in pump, which is 30.23 kJ over kilogram.
To calculate for the mass flow rate, we are going to use the formula work output of steam turbine in kJ per second divided by work output of steam turbine in kJ per kilogram. So we are going to assume that the work output of steam turbine is 50 megawatt. So we are going to divide it by 1662.34 kJ per kilogram and we will get the value here, which is 30.0781 kg per second. So this is for one steam turbine. Since we are using 3 steam turbines, we are going to multiply it with 3 and we will get 90.234 kg per second. And now for the work input of the pump, we are going to multiply the mass flow rate with the work input of the pump we obtained earlier. So we are getting the value 2727.774 kilowatt. And for the work net output of the steam turbine, we are going to subtract work input of the pump from the work output of steam turbine. So as we see here, we will get the value 147.272 megawatt of work net output for 3 steam turbines. Now for the rate of heat rejected by the condenser, we are going to use energy balance equation. seen here, and we are going to be left with the Q net out equals to H2 minus H3. So we input the values that we obtained earlier, and we will get, for the Q net out is 1914.029 kJ per kilogram. And for the rate of heat rejected, we are going to multiply the value that we obtained earlier with the mass flow rate of 3 steam turbine, and we will get the value 172.17 megawatt of heat rejected. For the volume flow rate of steam, we are going to use the formula mass flow rate of 3 steam turbine times with V1, which we obtained earlier. As we can see here, we are going to input the values, and we will get the volume flow rate equals to 4435.398 meter cube per hour.
Next, we will be calculating the rate of heat received by combustion chamber QH. Since the process of combined gas steam power plant is in steady flow state, energy in equals to energy out. From the energy balance, we can expand it into Q in minus Q out equals to W out minus W in. Hence, the energy balance of the combined gas steam power plant is Q net in equals to W net out. Based on the conditions given, the aim for electricity produced is 500 megawatt, thus W net out equals to 500 megawatt. Since Q net in is equals to W net out, Q net in is also 500 megawatt. Q net in can be obtained through the formula of QH minus QL. From previous calculations, QL is 172.71 megawatt. After rearranging the equation, QH is 672.71 megawatt. To find the work input for compressor, we can use the following equation. The value assumed for work output of gas turbine is 400 megawatt. Through the substitution of values, W in compressor is 44.544 megawatt. We also need to find the mass required for coal. Based on reference, we chose sub-bituminous coal as the fuel since it has a low sulfur content. The heating value for sub-bituminous coal is 23.9 megajoule per kilogram. The value for mass of coal is found using the following formula. Hence, the mass of coal required for 1 second is 28.1147 kilograms. For the overall thermal efficiency of the combined gas steam cycle, we shall use the formula as shown. For previous calculations, the value obtained for Q out is 172.71, while for Q in is 672.71. Thus, the value for thermal efficiency is calculated to be 0.04.
The actual work produced for each device is calculated. The isotropic efficiency for each device is as shown on the slide. For steam turbines, the actual work produced is calculated based on the following equation to obtain a value of 132.545 megawatt. The actual work produced from gas turbine is calculated based on the equation shown, and the value obtained is 360 megawatt. The actual work input for compressor, on the other hand, is calculated based on the equation shown, and a value of 53.667 megawatt is obtained. Lastly, the actual work input for pump is calculated based on the equation shown, and a value of 3.031 megawatt is obtained. From the actual power produced for each device, the actual net work output for combined gas steam power cycle can be obtained using the formula as shown. The calculated value would be 435.847 megawatt. And lastly, to calculate the back work ratio, the ratio of compressor and pump work to turbine work, the following formula is used. After substituting the values, the value of backward ratio is 11.51%.
The backward ratio is usually quite small in steam turbine power plants as the working fluid is water and the specific volume of water is smaller compared to air, which is used in gas turbines. Based on the explanations and calculations above, this gas steam cycle is a Rankine cycle. A Rankine cycle is a steam engine in which the water is boiled, evaporated, used for work and then condensed for reuse, making it a closed cycle. Thank you.